This is chapter 4, part 2, moving on from slide 12. So we're going to continue doing the same thing for MA models in terms of the backshift operator that we just did for AR models. So now we're going to have psi of x being a polynomial of order q, which is going to have this form 1 plus psi x plus psi 2 x squared plus psi q x to the q. And this time we don't have the minus signs that we needed for the autoregressive polynomial, because then we can write the MAQ equation M3 just as yn is psi of b epsilon n. Now, how do we do this for an MA infinity process? There's an interesting thing we can do here with Taylor series. So if we have any function g of x, we can write a Taylor series. G of x is g0 plus g1x plus g2x squared plus so on. And this lets us make sense of writing yn equals mu plus g of b epsilon n. It's kind of a weird thing to think about, because you can get having powers of the lag operator is maybe a reasonably natural thing to do, but what does it mean, say, to talk about log of b? Well, log of b doesn't seem to make much sense, but if you can expand log by, or log 1 plus b or something by a Taylor series expansion, and then you know how to make sense of an MA infinity representation, then you can make sense of an arbitrary function of the lag operator. This means that this is useful to do, and it means that whatever you know or learn about working with Taylor series expansions helps you understand AR, MA, and ARMA models, as we'll see. Now, you probably have all seen Taylor series expansions, some more than others, some recently, some long time ago, but it's we're going to find it's useful to brush up on them. Okay, so now we can put together these two AR and MA parts, and here we have a general autoregressive moving average PQ model, which I've written in full in M9. It's just the general AR and the general MA put together. And that's a long equation, M9, hard to fit it on a line, but if we use the backshift operator, you just write it as phi of b yn is psi of b epsilon n, and it's very compact. Now, we've seen a little bit that AR models can be natural for describing oscillatory behavior, maybe some other things. MA models, it's a little bit less clear why you would want to write down an MA model, but it's a statistical fact based on experience with data analysis that often when you do data analysis, it turns out to be good to have both an AR and an MA component. And that's something you will get to experience yourself when you do data analysis. You can see whether you agree with that statement. Okay, one thing in M9 that I didn't do and I haven't done yet in previous ARMA models is included a mean. When you are using the backshift operator, you can write the mean into the model very succinctly as phi of b yn minus mu is psi of b epsilon n. So that just means that yn minus mu satisfies this ARMA model. Okay, so now we're going to start using this Taylor series expansion idea to find the MA infinity representation of an ARMA 1-1 model. And remember, once you found the MA infinity representation, you've also found the covariance, the autocovariance, because that's quite easy to get once you have the MA infinity representation. So this is an interesting calculation. The ARMA 1-1 is a useful model, but it's also an interesting method because you can use it in other situations. So if we want an MA infinity model, we're going to use this Taylor series expansion trick. We want to put the model in the form yn is g of b epsilon n, where g is some function we're going to work out. Well, we know the ARMA 1,1 model is 1 minus phi b yn is 1 plus psi b epsilon n. And this is at least algebraically equivalent to dividing through by 1 minus phi b, whatever that means. And we get yn is 1 plus psi b over 1 minus phi b epsilon n. Or yn is g of b epsilon n, where g of x is 1 plus psi x over 1 minus psi x. Now, you recognize this from our discussion of general Taylor series, right? If we find the Taylor series expansion of g of x as essentially an infinite polynomial, then we can interpret that as a function in the lag operator. Now, I'm not going to work through the details by hand right now. This is something that one can either do by hand or using your favorite math software, and how familiar you are with Taylor series expansions decides whether this is easy or difficult. But once you have that Taylor series expansion, you have the MA infinity representation, and then you can use the general formula for autocovariance of an MA infinity to find the autocovariance function of the AR1, and that's an exercise. Okay, so we talked about causal, the definition of causal for a linear process. We've seen that an ARMA model has an MA infinity representation. And so we say that the ARMA model is causal if its MA infinity representation is causal and convergent, because if its MA infinity representation isn't convergent, then that's not really a very satisfactory representation. Okay, so causality is about writing the yn in terms of the driving noise process epsilon n. We can also define invertibility, which is basically the reverse task, writing epsilon n in terms of the time series process yn. And assessing causality means writing yn in terms of epsilon n. That's basically what we just did before. We write yn is psi of b over phi of b epsilon n and calculate the Taylor series expansion, see if it converges. To look at invertibility, you just have to do essentially the same thing, but the other way around. Epsilon n is phi of b over psi of b yn, and so you're doing the Taylor series expansion, but on the inverse, the ratio the other way around. Okay, so at least in principle, we know how to check for causal and invertible properties of ARMA models based on Taylor series expansions. You can do that, but fortunately, there's a simple way to check causality and invertibility without calculating the Taylor series, and here's how to do it. So I'm not going to say exactly why this is true, but it's something you can think about to try and get some intuition. So the ARMA model is causal if the autoregressive polynomial phi of x has all its roots outside the unit circle in the complex plane, and a root is a solution to phi of x equals 0. And so that's something that one can check. Sometimes you can find the roots by hand. If p is larger than 2, that may often be hard to do, and so it's nice to have software to do that for you. And then the corresponding property for invertibility, rather than having the AR polynomial with roots outside the unit circle, you need the MA polynomial with roots outside the unit circle. And polyroot is the function in R to do that. So let's just calculate one example. If you have the MA2 process, yn is epsilon n plus 2 epsilon n minus 1 plus 2 epsilon n minus 2, then you first of all calculate the MA polynomial, which is phi of x is 1 plus 2x squared, and then you calculate the roots using the polyroot function, and here they are. And you see, in fact, that they're both inside the unit circle, they're not outside, and so the moving average model is, in this case, not invertible. Here you go. You can do abs roots to check that calculation. And again, in this particular case, it's a quadratic, so you could find the roots by hand, but in practice, it's more general just to use the software polyroot. Now, maybe you have some idea why it's nice to have a causal model, because you want to think that the data are somehow generated by some process that combines past noise. Why do you want to have an invertible model? What's wrong with a non-invertible model? Like the model that I just wrote down on the last slide, yn is epsilon n plus 2 epsilon n minus 1 plus 2 epsilon n minus 2, seems a perfectly good model. Why might we not want to use that model if it's not invertible? Well, one answer to this question involves diagnosing model misspecification. And so if you think about what it means to be invertible, let me just write this down. If we have a non-invertible model, what happens to the estimates of the residuals? The estimates of the residuals come from applying, we have this identity epsilon n. Well, the residuals are really the estimates epsilon n hat. The natural way we would estimate the residuals would be to take the MA infinity representation coming about by the Taylor series expansion of psi of B inverse and apply it to the data yn star. And then this is not stable since non-invertibility implies let me just get my pen back. The coefficients in the Taylor series expansion of psi of B inverse are growing, right? So when you try and calculate the residual, you're going to take some linear combination of lags. It's stable if that linear combination becomes, if the combination, as you go further and further away, you have less and less role for the data. Here, as you go further and further back in time, there's growing role of the data, and so if you try to truncate that Taylor series expansion, for example, you would be missing out on something that just keeps growing on you. Okay, so that's why invertible models are convenient to work with. Another thing that we can do to find desirable properties of ARMA models using what we know about the algebra of the AR and MA polynomials is something called reducibility. So if we look at this ratio, yn is phi of b over psi of b epsilon n, well, phi of b and psi of b are polynomials. They might share a common factor. And if they do share a common factor, it can be cancelled out without changing the model. And common factors of polynomials is equivalent to common roots. And the reason that's true is the fundamental theorem of algebra, which says that a polynomial is determined by its roots. You can write it as essentially a product in terms of its roots. And then the factors cancel if and only if the roots are the same. And so let's think about what happens if, in practice, if the roots are the same. Well, here's also a little note on the Taylor series expansion being convergent. So some intuition for why the convergence of the Taylor series expansion is equivalent to having all the roots outside the unit circle. If you think of the polynomial as the product of its roots, and you take the inverse of the polynomial, you have a product of the things like 1 minus b over lambda I inverse, and that expansion, that Taylor series expansion of 1 minus b over lambda I inverse is fairly well known to be stable only if the absolute value of lambda I is greater than 1. Okay, so we pointed out that these polynomials share a common factor if and only if they share a common root. And one of the nice things about knowing that math is that if you just try to look at the, say, the fitted model, it might be very unclear that you have two models that are essentially the same because they share a root. And here's two in equations 23 and 24. And unless you have much better intuition than me, you wouldn't see immediately that these are essentially the same model. You have to do the math. You calculate the roots of the AR and the MA in equation 23, and you see that they both have a root of 2. And so that means that 1 minus 1 over 2b, 1 minus a half b is a factor that cancels out in both cases. If you do cancel it out, you get 24. Okay, so we're going to do a little bit more with the backshift operator in using it to investigate a model in part 3, but this is the end of part 2.